Chapter 6.1, we are starting antidifferentiation. So far we've been coming up with several techniques for calculating derivatives, such as power rule, product rule, quotient rule, chain rule. So we've been finding the derivative f prime of a function f. Now what we're going to be doing, just like the name antidifferentiation suggests, we're going to be going in the reverse direction, essentially going backwards. We're going to be starting with the derivative of a function, and then we have to find the original function itself. So the process of going from f prime to f is called antidifferentiation. So this definition here pretty much just says exactly what we just mentioned, so I'm not going to say that again. But there's a couple important theorems that we're going to be taking into account when we're doing antidifferentiation problems. And the first one here, without reading this and making it sound confusing in here, is that let's say that we want to take the derivative, I'm just going to put example, if we want to take the derivative of 1/3 x cubed plus 2. So taking the derivative here, that would end up being, you bring the 3 out front, but it cancels with the 1/3. Subtract 1 from the exponent, we get x squared. And the derivative of 2 is 0. So the derivative here is x squared. So we might try to say that the antiderivative of x squared is 1/3 x cubed plus 2. But if we take the derivative of 1/3 x cubed minus 7, we end up getting x squared plus 0 again, so we get x squared. So notice how if we keep on doing this, but we change the constant, that we'll keep on getting the same derivative, so the constant doesn't matter. So when we're taking the antiderivatives, we are always going to be adding on this constant here at the end. So the antiderivative of x squared is 1/3 x cubed plus c, where c is just some constant. Like we just showed on the left, it could be 2, it could be -7, it could be anything. Okay, so that's something to keep in mind here, because we're essentially going to have it in every single one of our antiderivatives. And that sort of brings in theorem 2 here. So let's see an example. If we want the derivative of 7, let's say, the derivative of a constant is 0. And then let's say we want the derivative of -3. The derivative of the constant is 0. And we can keep on going. The derivative of any constant is 0. So if we're trying to find the antiderivative of 0 and we're trying to go in the reverse direction, we can't say the antiderivative of 0 is 7. We can't say that the antiderivative of 0 is -3. All we can say is that the antiderivative of 0 is some constant. Okay, so those are just a couple important concepts that we will be using for essentially every single problem here. So starting with the indefinite integral. The indefinite integral is essentially the notation that we're going to be using to find the antiderivative of a function. So here is the notation right here. We use that symbol. That's called the integral sign. And the entire notation itself that I circled is called the indefinite integral. And like I mentioned, it stands for finding the antiderivative of the function f of x. So one thing to keep in mind here is this dx here. That's a differential, and it just means that we're doing this integral with respect to x. Anytime you have an integral, you need that differential all the way at the end every single time. Okay, and then just one more little terminology here. In the integral of f of x dx, the function f of x is called the integrand. Okay, so let's just see a little example here. Let's say we are taking the derivative of x squared. We know that equals 2x, so d dx of x squared equals 2x. And let's say we are doing the integral of 2x, and then remember you always need dx. So we're finding the antiderivative of 2x, which if you just go backwards from what we just did, we would know that that's x squared, and we need that plus c every single time. So you can see how these are related. They're the same thing, just in the reverse direction. And make sure you know notation for both of them. Okay, so here are a couple of very, very important rules that we're going to be using. First one is the power rule. So if we're taking the integral of x to the r, where r is a number, not equal to -1, so the integral of x to the r dx, what we have to do is we have to add 1 to the exponent and then divide by that new exponent. And notice that all of these have plus c, just for the same reason why we mentioned before. So it's the exact opposite power rule that we use for differentiation. Next is the exponential rule. If we're taking the integral of an exponential e to the kx dx, then it's going to stay the same, and then we're going to divide by whatever that k number is. And the only one that's a little bit less obvious is if we take the integral of 1 over x dx, that's when we get the ln of the absolute value of x. So a few things for this one. The reason for this is because the derivative of ln of x is 1 over x. We have to be careful though. We need these absolute value signs. So the original integrand 1 over x did not specify that only had to be positive. We could have x be negative. 1 over a negative number is completely fine. However, when you have ln, you cannot do ln of a negative number, so we have to specify that it has to be positive. Okay, so these are 3 things that you just have to have memorized. So let's do some examples here. We want to determine the following. The first one is the integral of the square root of x dx. And let's go ahead and rewrite this as the integral of x to the 1/2 dx, because the square root has a 1/2 exponent. Now this is going to be power rule. So what we have to do is we add 1 to the exponent. 1/2 plus 1 is 1/2 plus 2/2, which is 3/2. And then you divide by 3/2. Instead of dividing by 3/2, multiply by the reciprocal, which is 2 over 3. And then as usual, we go ahead and add some arbitrary constant, and that is the integral. So what you can do, which you don't always have to do this, but for now let's go ahead and check our answer. Let's differentiate our answer and see if we get what we started with. So this is obviously going to be power rule. Bring the exponent out front. So that's going to be 2/3 times 3/2 x. Subtract 1 from the exponent, we get 1/2. The derivative of c is the derivative of a constant, which is 0. 2/3 times 3/2 cancel. We're left with x to the 1/2, which is the square root of x. So we're good, because that's what we started with. Okay, and let's see one more here for using power rule. So this, we have to rewrite this one as well. We need to rewrite it as x to the -2. So before applying the power rule, it has to be in the numerator. To do that, you make the exponent negative. Now we take the integral of it, add 1. -2 plus 1 is -1. Divide by -1. So we could write that as 1 over -1 if you want, and plus c. And then we simplify this. That gives us -1 over x to the +1. So -1 over x plus c. And I'll leave it to you guys to check that, take the derivative of that, make sure you get 1 over x squared. And next one for c, we have the integral of e to the x. So this is obviously an exponential rule. And for this rule, all we have to do is recognize that this is e to the 1x. So based on the exponential rule from a couple pages ago, you're going to rewrite it and then divide by the constant. So I'm just going to write the rule here. The integral of e to the kx dx equals 1 over k e to the kx plus c. Our k value here is 1, so we don't need to write that. So our answer is just e to the x plus c, which we know is true. The integral of e to the x is e to the x because the derivative of e to the x is e to the x. And let's do one more of these ones. And this is the integral of 1 over x. Little bit tricky for this. You have to know that this is not the power rule. It looks like you can do something similar to what we did to 1 over x squared when we took the integral of that a few pages ago. Not the same thing. When it's 1 over x, when the exponent is 1 on x, this is when you get the ln of the absolute value of x. And then plus c, once again, this is the log rule because it's 1 over x. The exponent on the x is a 1. If it's not a 1, then it becomes the power rule. When it's a 1, it is the natural log of the absolute value of x plus c. Okay, and then here are a couple properties that hopefully are kind of obvious when we're evaluating integrals. If we are evaluating the sum or the difference of two or more functions, we can split them up and do them separately. And then if we have a constant that we're multiplying the integrand with, we can pull the constant out front and then take the integral and then multiply it afterwards. Okay, so let's apply the rules that we learned with those properties that we just mentioned in this one question. So this question is pretty much, it sums up everything that we just did so far in this section. We want to find the integral of x to the negative 3 plus 7 e to the 5x plus 4 over x. Let's go ahead and rewrite that. We have three different terms. That's going to be the integral of x to the negative 3 dx plus the integral of 7 e to the 5x dx plus the integral of 4 over x dx. So all we did was split them up, each term separately, and let's go ahead and evaluate each one. So the first one is the power rule. Before we do that, I'm going to rewrite this, and we'll see why in a second. The reason is because I'm going to take care of these constants that are on both of these other ones right here. I'm going to pull them out front. So it's going to be plus 7 times the integral of e to the 5x dx, and then plus 4 times the integral of 1 over x dx. So all I did was just pull out those two constants. Now let's take the integral of each one. So the integral of the first one is power rule. So we're going to add 1 to the exponent. Negative 3 plus 1 is negative 2. Divide by negative 2. And I'm going to write this one like this. Divide by negative 2. And now we have plus 7 times the integral of e to the 5x is e to the 5x divided by 5 plus 4 times the integral of 1 over x. That's the ln of the absolute value of x. So notice that I did not put plus c for each one. We can just put one big plus c at the end, and that's all we need. So we could clean this up a little bit. Let's write this as negative 1 over 2x squared plus 7 fifths e to the 5x plus 4 ln of the absolute value of x plus c. And that looks pretty clean. So there is our antiderivative. Okay, so we had to use both of those properties that we just mentioned on this page, and we had to use power rule, exponential rule, and logarithmic rule. So we want to find f of x, where f prime of x is x squared minus 2, and f of 1 equals 4/3. So don't worry about this yet. We'll come back to this in a second. We have to use the fact that if we're given the derivative and we want to find the function, then we can take the integral of the derivative to get us the original function. So I'm going to write this like this: the integral of x squared minus 2 dx. And if you have more than one term that you're integrating, make sure you have parentheses around them. So if we want to integrate that, the integral of x squared is going to be x cubed divided by 3. And then the integral of negative 2 is negative 2x. And then we need this plus c. So something that's important that I don't know if we saw yet, if you're taking the integral of a constant, the integral of c dx, it's always going to, I should write that as k. It's always going to be kx, and I'm just going to put plus c. I'm writing this because if you have a constant and you're integrating it, you're just going to multiply an x on, and that's going to be the integral. So what we just found f of x. F of x was the integral of its derivative, which should make sense. The integral of a derivative, they essentially cancel each other off, and we get this right here. Now we need to take this into account. F of 1 equals 4/3. We're going to use this to find c. We're going to use this to find the constant, because right now the constant can be any number, but this condition has it so we have to find an exact value of c. So let's go ahead and say f of 1 is 4/3, and we plug in a 1 into all of the x's. So 1/3 times 1 cubed minus 2 times 1 plus c. And we go ahead and solve this for c. So that's going to give us 4/3 equals 1/3 times 1 is 1/3. 1/3 minus 2 is 1/3 minus 6/3, so that's negative 5/3. Just adding or subtracting fractions, you need common denominators. And we have to add 5/3 to the left. So c is 4/3 plus 5/3, which is 9/3, which is 3. So for the final answer now, we have to go back up here and plug a 3 in. So that's going to be f of x equals 1/3 x cubed minus 2x plus 3. So what we just did is we found the function f of x such that the derivative is x squared minus 2 and f of 1 is 4/3. And you can check that by finding the derivative. And here are a couple antiderivatives of x squared minus 2. And you can see that they all have the same slope at each point. They're all written here with different c values. So they're all just vertical shifts of each other when we give them different values of c. So the one that we wanted for this particular one was c equals 3. So that one was our answer here. Okay, one more example here. We have the position function s of t is the antiderivative of velocity v of t. We want to find the position function such that the velocity is t squared over 5 minus 6t plus 0.5. So we're going to know that the position function is the integral of this velocity function, t squared over 5 minus 6t plus 0.5. And our variable this time is t, so we put dt instead of dx. So taking the integral here, that's going to be, I'm going to write this as 1/5 we're going to add 1. Actually, I'm not going to write it as 1/5. We're going to add 1 to the exponent. So 2 plus the 1, we get 3. And then we divide it by 3 minus, we're going to add 1 to the exponent, divide by that new exponent. 0.5 is a constant, so that's 0.5 times t, and then plus c. And we have to simplify this. That's going to be t cubed over 15, or 1 over 15 times t cubed, however you want to write it. 6 over 2 is 3. And that about cleans it up as much as we can. So that is our function s of t. We don't have any other condition that we have to satisfy to solve for t, or solve for c rather. So that is our answer. Okay, so that is it for this chapter.